Ever pondered about the fabric of the universe? What if we told you that space and time aren't separate entities, but intertwined into a four-dimensional continuum known as spacetime? This isn't a plot from a science fiction novel, but the reality as we understand it today. This concept, mind-bending as it may seem, is a fundamental pillar of our understanding of the universe. It's like the stage upon which all cosmic drama unfolds. But what if the stage itself is a character, actively participating in the play? This is where the enigma of spacetime comes into play, a concept that stretches our imagination to its limit and beyond. It challenges our intuitive understanding of reality and invites us to see the universe through a different lens. To comprehend this entanglement, let us dive into the world of Albert Einstein's theory of relativity. Our journey begins in 1905 with Einstein's groundbreaking special relativity. This was the year when young Albert Einstein, a patent clerk at the time, shook the very foundations of physics. He presented a theory so revolutionary, it dared to reimagine the classical notions of space and time we had inherited from Newtonian physics. The heart of special relativity rests on two simple yet profound postulates. The first postulate states that the laws of physics are the same for all observers in inertial frames of reference. Whether you're sitting still on a park bench or zooming past in a super-fast train, the laws of physics remain unchanged. Let's pause for a moment to appreciate how radical this idea was. It meant that there's no absolute state of rest or motion. Everything is relative. The second postulate is even more counterintuitive. It asserts that the speed of light in a vacuum is the same for all observers, regardless of their relative motion or the motion of the light source. That's right, if you were racing alongside a beam of light, it would still whiz past you at around 300,000 kilometers per second. This constancy of light speed was a departure from the classical understanding, where speeds simply added up. These two postulates, as straightforward as they may seem, had far-reaching implications. They led to some mind-boggling predictions, some of which defied our everyday experiences and intuitions. They suggested that space and time were intertwined in a four-dimensional fabric called spacetime. They implied that time could dilate, and lengths could contract depending on the relative motion of observers. These radical ideas were just the beginning of Einstein's transformative journey. From here, he went on to formulate the theory of General Relativity, which added gravity into the mix and further revolutionized our understanding of the universe. But that's a story for another scene. For now, let's marvel at the sheer audacity of special relativity and the way it forever changed the way we perceive reality. Among the revolutionary outcomes of special relativity was the iconic equation E=mc². This equation, simple yet profound, reveals an intrinsic connection between energy, E, and mass, m, with c representing the speed of light in a vacuum. Essentially, it tells us that energy and mass are interchangeable, two sides of the same cosmic coin. This energy-mass equivalence was a game-changer in the world of physics. It suggested that a tiny amount of mass could be converted into a tremendous amount of energy, and vice versa. This insight laid the foundation for the development of nuclear energy, where small amounts of matter are transformed into substantial energy. Moreover, this equation significantly altered our understanding of the universe's energy dynamics. It hinted at the vast energy potential locked within matter, opening up new avenues in our quest to comprehend the cosmos. This equation laid the groundwork for further exploration of the universe's intricate workings. Special relativity also introduced fascinating concepts such as time dilation and length contraction. Let's start with time dilation. Imagine you're moving at high speeds, perhaps aboard a spaceship cruising near the speed of light. To a stationary observer, your clock appears to tick slower. This is time dilation, a rather peculiar effect where time seems to slow down for an observer in motion relative to a stationary one. Now, onto length contraction. This intriguing phenomenon implies that to a stationary observer, an object moving at significant speeds will appear shorter along the direction of motion. It's almost as if the universe is squishing the object as it speeds along. Both these concepts have been experimentally verified. with time dilation being a critical factor in the functioning of particle accelerators, and length contraction providing intriguing insights into the behavior of high-speed particles. These relativistic effects further challenged our understanding of spacetime. Einstein's quest to understand gravity led him to the formulation of general relativity in 1915. This remarkable theory expands our understanding of gravity far beyond the realm of Newtonian mechanics. But what does that mean, exactly? Let's delve deeper. Instead of viewing gravity as a force acting at a distance, Einstein envisaged it as the curvature of space-time caused by the presence of mass and energy. This revolutionary idea presents a new perspective. Imagine space-time as a flexible, four-dimensional fabric. When a massive object like a planet or a star is placed on this fabric, it causes a dip or a curvature. Now, smaller objects moving on this curved space-time will follow paths influenced by this curvature, a phenomenon we perceive as gravitational attraction. So, instead of a mysterious force pulling objects towards each other, gravity is a consequence of the way mass and energy warp the fabric of space-time. It's like a marble rolling around a funnel. The marble, representing a smaller object like a planet, follows the curves of the funnel, representing the space-time warped by a more massive object like the sun. But there's more. Einstein's general relativity also predicts an intriguing phenomenon known as gravitational time dilation. This states that the stronger the gravitational field, the slower the time ticks. This means that clocks placed in strong gravitational fields, like near a massive star, will run slower compared to those in weaker fields. In essence, general relativity ties together space, time, and gravity into a unified dynamic entity, the space-time fabric. It's no longer about objects acting on each other across the void of space. Instead, it's about how objects shape the space-time around them and how this curved space-time, in turn, governs their motion. General relativity revolutionized our understanding of gravity from a force to a geometric property of space-time. It's a leap that has forever transformed our perception of the cosmos, making it one of the most profound intellectual achievements in the history of human thought. Over the years, numerous experiments and observations have validated Einstein's theories. Let's take a trip down memory lane. In the early 20th century, during a total solar eclipse, astronomers measured the bending of starlight as it passed close to the sun. This remarkable observation provided empirical evidence for the curvature of spacetime, a key prediction of general relativity. Then there's gravitational lensing, a fascinating phenomenon where the gravitational field of a massive object bends light from a distant source, similar to how a lens refracts light. This makes it possible for us to observe galaxies that are behind massive objects from our perspective. Remarkably, this was another prediction by Einstein, and countless instances of gravitational lensing have been observed since its first detection in the 1930s. These confirmations have cemented Einstein's theory of relativity as a cornerstone of modern physics. General relativity's predictions extend to the existence of black holes and the concept of singularities. Black holes, these phenomenal cosmic entities, are regions in space-time where gravitational forces are so intense that nothing, not even light, can escape their pull. This makes them invisible to the naked eye, detectable only by their gravitational effects on surrounding matter and the distortion they cause in space-time. Black holes are the ultimate manifestation of Einstein's theory, demonstrating the extreme warping of space-time caused by immense concentrations of mass and energy. At the heart of a black hole, we encounter the fascinating and somewhat unsettling concept of a singularity. Singularities are points where the laws of physics as we know them break down. The density becomes infinite, and space-time curvature reaches its maximum. They are the ultimate enigma, a place where our current understanding of physics is insufficient to explain what happens. The existence of black holes and singularities has profound implications for our understanding of the universe. They challenge our comprehension of reality, pushing the boundaries of what we consider possible. They raise questions about the nature of space-time, the flow of time, and the fate of matter under extreme conditions. Moreover, Black holes serve as excellent testing grounds for theories that seek to unify quantum mechanics and general relativity, two of the most successful yet incompatible theories in physics. They also hold clues to the mysteries of dark matter and dark energy, elusive components that make up over 95% of our universe. While black holes and singularities may seem like abstract concepts, they are very real aspects of our universe. Observations of black holes, such as the historic image of the black hole at the center of the M87 galaxy, continue to validate Einstein's predictions and provide us with valuable insights into these cosmic phenomena. In the end, Einstein's theory of relativity has reshaped our understanding of the universe, opening doors to new realms of exploration and discovery. We stand on the precipice of these new frontiers, eager to delve deeper into the unknown, propelled by our insatiable curiosity and the enduring legacy of Albert Einstein.